Hey party people, we're going to get into scientific notation. What's up? Now we're doing the unit on exponents and laws of exponents, and it totally fits that we should talk about scientific notation because guess what scientific notation deals with? Exponents. Good guess. Now what we're going to do to learn scientific notation is work on these 5 crazy looking expressions, and we're going to simplify each of them, and we're going to use scientific notation to do it. Now hopefully this is not the first time you've seen scientific notation, but even if it is, hopefully we can learn some more stuff about it. We're going to work with it. There's some crazy things that are going on here for each of these problems. If you look, each expression has its own type of craziness that's happening, and we'll work with each one. To begin, we probably want to learn a little bit more about scientific notation. Like, for example, what is it? So let's talk about scientific notation for a second. Scientific notation is basically a way of condensing very, very, very big numbers or very, very, very small numbers. Because in the actual world, the world of science, the numbers we deal with have a tendency to be extremely huge or very infinitesimally small. And we use this notation to condense how we're writing, because we don't want to spend time crunching numbers that have 1,000 different zeros in either of the two directions. So here's a couple of examples. Did you know that the distance between the Earth and the Sun is 150 million kilometers? Okay, so that's a big, big number. And if we're going to start crunching numbers with this particular science fact, we don't want to have to write all those zeros every time we work with that. So we use scientific notation. And the way that happens is that we can take a number like 150 million and condense it. And we have to use some standard rules. So we have 150 million, and the way scientific notation works, if you're unfamiliar, is that we identify currently where the decimal is. Okay, so if you look at a number like this, we're looking for the decimal, right? So where in the world is the decimal in this number? Everything with scientific notation deals with place value. So we have to figure out, well, where in the world is the decimal? So when you look at a number like this, the decimal actually exists right here. There is the decimal. So the decimal exists there. What does that have to do with anything? Well, the way scientific notation works is that you have to have the decimal after the ones place in the expression. So the decimal has to be in the ones place after the expression. What is that? Whatever that means. So if we're to move a decimal to where the ones place would be, if the digit 1 for the 150 million representing the 100 millions place, if that's the 1, if I'm to make that the ones place, it would look like this. It would look like 1.5, right? So we'd have to somehow make that decimal from here over to here to put it in the ones place. And then we have to express it as a multiplication of a certain number of tens. Now why tens, right? Because place value deals with tens. We're human beings. We have 10 fingers, 10 toes. We work in base 10 number system. So we're going to talk about scientific notation with tens. So we have to figure out what just happened with this number. How many places did it move to multiply by tens? Because each place is a 10, right? So we have the tens place, the hundreds place, thousands, 10,000, tens place, ones place, tens place, hundreds place, thousands place, 10,000s, 100,000s, millions, 10 millions, 100 millions. So each place, starting with the ones, each place value is worth 10 times. So once you get to 10, we move on to the next place. This is why the abacus is so cool for learning numbers. But anyway, neither here nor there. So we have to figure out how many places should this decimal move to make it there, right? And so we count how many places it went. 1 place, 2, 3, 4, 5, 6, 7, 8 places. So in fact, if we're to rewrite this as this, we'd be multiplying 1.5 times 10 to the 8th power. And so that is scientific notation. We have now expressed this very, very huge number in a more compact manner. Okay, and that's the whole purpose of scientific notation. So we have to remember how that works. Now, let's think about this in terms of exponents. We know that 10 to the first power is equal to 10, right? And we know that 10 to the second power is equal to 100. And we know that 10 to the third power is equal to 1,000. So let me ask this question. Do you remember what 10 to the negative 1 power might be? Okay, do you remember what 10 to the negative 1 power might be? Laws of exponents, right? A to the negative n is 1 over a to the positive n, right? So 10 to the negative 1 power is actually 1/10. It's actually small. And what is 1/10? 1/10. As a decimal, 1/10 is this, right? And so 10 to the negative 2 power is actually 1 over 10 squared, which is 1 over 100, or 1/100th, or equal to 0.01. And so we know our places, right? The tenths, the hundredths, thousands, 10,000s, 100,000s, etc., etc., etc. So we have to keep this in mind. So let's take a look at point 1. Point 1, we know as a matter of fact, is 10 to the negative 1, right? How are we going to write that in scientific notation, where the decimal has to be in the ones place, right? So how could we write this in scientific notation? We'd have to move that decimal over one place. So it would actually be 1 times 10 to the negative 1 power. That's 1/10. So 1 times 10 to the negative 1 power is actually equal to 1/10. Okay, so we took that 1. It's actually 1/10. How does that happen? Some interesting stuff. That's exactly how it's all related. Okay, so if I were to use scientific notation, 1 times 10 to the negative 1 power is actually 1/10. We know that from all this stuff. It all has to do with moving the decimal. So again, that's review. So let's talk about negative exponents again in depth. Again, we're talking about science. Did you know that the diameter of a helium atom is 22 something really small centimeters, right? So if you measure it in terms of centimeters, that's pretty dang small. So if we're going to use this fact and do some math with it, we have to be able to express it in a more condensed manner. So we're going to rewrite this number. I got 1, 2, 3, 4, 5, 6, 7, 0, and then a 22. How do I write that in scientific notation? Well, if you remember, we have to have the decimal represented in the tenths place. Okay, so or after the ones. So the decimal has to be represented this way, times 10 to some power. Okay. Now here's what we know. We know that if we're dealing with something smaller than 1, it's going to have a negative exponent. Something smaller than 1 is going to have a negative exponent. And guess what? This is smaller than 1. And if it's smaller than 1, it's going to have a negative exponent. Let's go ahead and write that down because that's pretty important. And so now what we have to do is count how many tens places it has moved from here to make it here, and it's going to have a negative exponent. So how many places did this move? It moved 1, 2, 3, 4, 5, 6, 7, 8 places. And so we're going to have 2.2 times 10 to the negative 8. And that is how scientific notation works. Okay, it takes a very big number or a very small number and condenses it so that we can work with it. If you've ever seen the movie Avatar, when the doctor is talking about the number of synapses and the trees and all that stuff on the planet, she actually uses scientific notation, which is kind of cool. So it exists. So when am I ever going to use this? If you're paying attention to Avatar, I guess is one way. So far, so good, I hope. Now what we can do is start using this to make some shortcuts. And here's some shortcuts. What we can do is take some numbers that kind of look like they're in scientific notation, but they're not really in scientific notation. So here's 2 examples of numbers that looks like scientific notation, but it's not. So how can we fix these and make sure they're in scientific notation? I'll show you the long way, and then we'll get to a shortcut. If you look at this number, 26.4 times 10 to the negative 4 power, we see that negative exponent. We know this number is going to be smaller than 1. Okay, so this number is going to be smaller than 1. And what that means is we have to move the decimal to the left. Okay, so the decimal is actually going to move to the left 4 times. 1, 2, 3, 4. Holy cow, what just happened there? Well, what just happened there is we've had 2 empty spaces we need to fill in with zeros. Okay, so this number, 26.4 times 10 to the negative 4, is actually 0.0026. That is actually the number. And if we're going to fix this, because this isn't in scientific notation, if we're going to fix this number, remember we have to express it with the decimal point in the appropriate place. In the appropriate place. It has to be at 2.6, right? So times 10 to what power? Some negative number. It's going to move 1, 2, 3 places, so it's 10 to the negative 3rd power. So when I said to fix this number, 26.4 times 10 to the negative 4 is actually 2.6 times 10 to the negative 3. What just happened? So we took this number, 26.4 times 10 to the negative 4th power. We had to move the decimal 1 place to the left, and somehow this number increased by 1. It went from negative 4 to negative 3. It's actually increased by 1. So it's 2.6 times 10 to the negative 3. If you have a hard time with this fix, do exactly what I did. Turn it into the big number first, the long extended number first, and then rewrite it into scientific notation. We'll do the exact same thing with this. Okay, so I say fix this. Here's this number, okay, 0.02 times 10 to the 5th power. That's not scientific notation. It has to be 2 times 10 to some number, and what is it? Okay, so to the 5th power means it's going to be bigger than 1. Okay, so it's a positive number. It's going to be bigger than 1. And so that means we're going to move this decimal 5 places to the right. 1, 2, 3, 4, 5. And that means we're going to fill in some zeros. So this number is actually 2,000. Okay, this number is actually 2,000. And now we're going to take that number 2,000 and write it into scientific notation. The decimal point is here, so we're moving it 1, 2, 3 places. So it's actually 2 times 10 to the 3rd power. Okay, so if we're going to fix this 0.02 times 10 to the 5th power, it's actually 2 times 10 to the 3rd power. Now it's in scientific notation. So remember, we started with 0.02 times 10 to the 5th. We had to move it 2 places this way, and then it becomes 2 times 10 to the 3rd. Actually the exponent decreased by 2. It's funny how that works. And if you have a hard time using this particular shortcut, feel free to write it out, and then you'll be able to fix some numbers. Because you'll see, when we're working in scientific notation, it doesn't always end up in scientific notation. We have to make things into scientific notation. Works with the decimal after the ones place. Okay, so that's all we're working with is the ones place. So that's pretty key there. That's the background and your notes on scientific notation. So that's the background information. Now what we can do is start hammering out these fun problems. Now we're going to start simplifying numbers using scientific notation. So we look at our first expression, and we see what's happening. What is happening? Well, we've got 3.6 times 10 to the negative 12th power times 6 times 10 to the 9th power. Notice everything I've said is times. It's all times, 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 times. So if it's all multiplication, guess what we can do? If it's all multiplication, we can start multiplying stuff, right? We can start taking care of multiplication and rewriting stuff. And if I have a similar base, I'm going to keep those right there. I can regroup this. It's 3.6 times 6. And then times 10 to the negative 12 times 10 to the 9th. That is totally legitimately possible. Okay? So it's all multiplication. I can just rewrite stuff. All I have to do now is basically crunch some numbers. So I have to multiply 3.6 times 6. Use your handy-dandy calculator if you need to. And you come up with 21.6. And then what do we do here? Right? It's that law of exponents. Use the law of exponents. A to the n times a to the m is equal to a to the n plus m. Okay, so we can use that law. If you remember the law of exponents, we can use it here, and that's going to be times 10 to the negative 12 plus 9 is negative 3. All right, so we have that thing. Since it's all multiplication, you can use the commutative property, and then we can use the law of exponents to get this. Now, you should be saying, but wait, this is not scientific notation. Not done yet. Why not? Because the decimal is in the wrong place. The decimal is in the wrong place. We have to move the decimal one more place to make the number 2.16. How is that going to impact the exponent? You can either remember from this little trick, if I'm moving it 1 to the left, it's actually growing by 1. The exponent's growing by 1. Or you can write the whole thing out, right? Write the whole number, 21.6 in negative third power, and then rewrite it back into scientific notation. Either way, you're going to have 2.16 times 10 to the negative 2 power. It's growing by 1. So when I simplify this expression, right, a very, very small number times a somewhat big number is still going to give you a relatively small number, okay? Because it's smaller, it's still less than 1, right? So that's how we'd work that. If it's all multiplication, commutative property, law of exponents, and then make sure we're writing it in scientific notation. And that's how we would handle that first expression. Okay? So the second expression now. Now we're going to work on that second expression. So we have 3 times 10 to the negative 7 power, all raised to the third power. More laws of exponents, right? We can totally use this. What's happening? We have a power to a power. So if you remember, if we have ab to the nth power, that's equal to a to the n, b to the n, right? That's that law. And then we have this law as well, a to the n to the mth power, that's a to the n times m. We can use these two laws of exponents. We can apply those two laws of exponents here. So what's happening? We have our first number, because this is multiplication, just like this is. Multiplication, 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 fine. So we have 3 raised to the third power, and then times 10 to the negative 7th raised to the third power. Okay, that's what this is. We can use the law of exponents for this. Now we can start applying some stuff. 3 to the third power is 3 times 3 times 3, or 9 times 3, or 27. Now 10 to the negative 7 to the third power, I'm multiplying the exponents. I'm going to have 10 to the negative 21st power. So this is my number, but that's where I'm at. But this is still not scientific notation. Right? Remember, we are not done, not done. So how is it that we can fix? How can we fix this number? We locate the current decimal place, which is right here, and move it 1. Okay, so the decimal has to move 1 place. So now we're going to actually have 2.7 times 10 to the, and how would that impact this exponent, times 10 to the negative 20th. It's going to increase by 1. So it's going to be to the negative 20th power. It's going to increase by 1. So this is actually the expression. Right? So we have a very, very small number. To the third power is going to be an even smaller number. Right? So that's how scientific notation is working. Pardon the light impact on this. The sun is shining through. So now we have expression number 3. Okay, so we have this next expression. Now we're using division. And it's going to be the same type of thing. Okay, so we can still use all these laws of exponents. And we're going to apply scientific notation to it. So what can we do with this? We can rewrite this as, well, 1.2 divided by 2 times 10 to the 9th divided by 10 to the 5th. That's totally legitimate. We can do that, okay? We can do that. So what we have to do here is remember some laws of exponents, right? A to the n over a to the mth is equal to a to the n minus mth. Here's a law that we're going to apply right here, okay? So first we can crunch some numbers, and if you need to use your calculator, I'm cool with that. 1.2 divided by 2 is actually going to be 0.6. And then we'd have, according to this law of exponents, 10 to the, right? It's going to become positive 14. Okay? This is going to be 0.6 times 10 to the 14th power. Okay? But that's what we have. But remember, this is not done, not scientific notation. This decimal has to move one place to the right. And if you remember, if we're fixing stuff, and we're moving the decimal one place to the, or places to the right, the exponent is actually decreasing. So if we're moving it one place to the right, the exponent is going to decrease by 1. So we'd have 6 times 10 to the positive 13th. And again, if you can't remember which way it moves, write it out the long way. Write that big, big number, and then rewrite it into scientific notation. So this huge number divided by this very, very small number gives us still a pretty bigger number, right? It's huge. Scientific notation, yay. The language of nature. So now we look at a problem like number 4. Now we're getting, well, this is almost unnecessarily complicated. So number 4, we have a decimal times a big number, and going to be divided by another decimal times a smaller number, and we're going to figure out how that works. So the easiest thing to do would be to write this into scientific notation first. Then we can start figuring some stuff out. For example, this first number, 0.0007, is actually 7 times 10 to the negative what power? 1, 2, 3, 4. 10 to the negative 4th power. And we're going to multiply that by 11,000, or 1.1, times 10 to the 1, 2, 3, 4th power. Isn't that cool? And then that's going to be divided by 0.001 is actually 1 times 10 to the 3, negative 3 power, times 1 times 10 to the 2, 3, 4, negative 4 power. So we actually rewrote that whole thing in scientific notation first, and now we can start using some laws. So in the numerator, I can multiply 7 times 1.1. So I can multiply 7 times 1.1. And then I can multiply 10 to the negative 4 times 10 to the positive 4. And then in the denominator, I can multiply 1 times 1. And then 10 to the negative 3rd power times 10 to the negative 4th power. Okay, so I can use the same two principles from number 1 and number 2 and number 3. So we can start crunching numbers. 7 times 1.1, of course, is 7.7. And then times 10 to the, keep the base, add the exponents. Negative 4 plus 4 is actually 0. Boom, boom, boom. And then in the denominator, 1 times 1 is 1. Times 10 to the, keep the base, add the exponents. Okay? And so now we're going to figure some stuff out. What's happening here? This is going to be some fun things you're about to see. What's going on with 10 to the 0 power? Well, if you remember this law of exponents, a to the 0 power is 1 law, we can apply it there. So what we're actually looking at is 7.7 times 1 over 1 times 10 to the negative 7. But hang on, we're not done yet. Another interesting law. Check this out. If you remember, another law of exponents, 1 over a to the negative n is equal to a to the n. Another law. What does that have to do with this? This 10 to the negative 7th means I can move the base 10 up to the top, up to the numerator, and has 7.7 times 10 to the positive 7th power. So the whole thing works out to be And guess what? That is scientific notation. Holy cow. Isn't that amazing? Isn't that so much fun? So I take this unnecessarily complicated thing, and there it is. And I can use scientific notation. I can condense very, very big or very, very small numbers. And that's how that works. And so one last example, because there's a lot of cool stuff that's going on with this one. We will have solidified our understanding of scientific notation. So we have in the numerator a small number times another small number, and in the denominator an even smaller number. And we're going to simplify this. We're going to use scientific notation. Okay, so remember all the things that we have applied, we're going to do it here. So first thing I'm going to use is the commutative property in the numerator. 2.6 times 4.8, and then 10 to the negative third times 10 to the negative fourth. And the denominator, well, there's nothing to do there yet. Okay, so now I have my expression set up. Just start using your handy-dandy calculator. 2.6 times 4.8, and you come up with 12.48. Okay, so we have 12.48. And then our tens. Keep the base, add the exponent, 10 to the negative seventh. And that's going to be divided by 1.3 times 10 to the negative 12th power. Okay? So I'll do the same thing that we did in number 3. Now I have this set up, I can start dividing. So I'm going to start dividing. 12.48 divided by 1.3. That results in 9.6. What a simple number to work with. And then our tens. Keep the base, subtract the exponents now. So negative 7 minus negative 12 is negative 7 plus 12, which is positive 5. So I'd have 9.6 times 10 to the 5th power. And guess what? That is scientific notation. If it wasn't, I could easily fix it. But all of these things turn out to be strange. Now, I want you to notice something. This number is pretty big, right? 9.6 times 10 to the 5th power, that's a big, big number. Where did it come from? Take a look at this. A small number times a small number divided by an even smaller number turns out to be a big number? Interesting, but true, right? So it's kind of cool how that works. So a small number divided by an even smaller number turns out to be big number. Anyway, that works out in regular fractions too, if you think about it. So I will end here. That's it for scientific notation. Funny how that relates to laws of exponents. I hope you had fun, or as much fun as I did, and I'm out of here.